Okay, thanks everyone. So we'll start our next talk now with Santiago Hernández, who's going to tell us about algorithmic chemical theory of the human mind.
Yes, can you hear me? Okay, yes, so my name is Santiago Hernández. I work in a private company that's called Algorithmics. I'm here on behalf of my boss and mentor, Hector. He asked me to come here and talk about some of the work we have done together. In this case, the title for my talk is for the algorithmic complexity theory of the human mind. So rather than give you here like a complete theory or pretend to have a complete theory for the human mind, I'm not going to give a glimpse of how such theory might look like and the motivation for such a theory. So let me start with a crash course of algorithmic impulsion theory so that everyone knows which tools I'm using here. And the main tool for the algorithmic complexity theory is called the algorithmic information complexity of an optical object. This is noted by the letter K, which is come from the formula, which was the first one to propose this measure. And this measure attempts to measure the complexity of an object given the size of the minimum computer program that describes it. So one of the properties of this measure is that it's independent of the computer program, the computer model you are using. And the only difference between two different computer models is that it's a constant, which is the compiler, the translation layer that can translate one language to the other. So it's very robust in that sense. Now, the reason why on the wall of, sorry for that. So the reason why on the wall decided to dig into the computer realm in order to answer a question of probability is he was looking for a definition of a robust definition of random objects, and this is the definition which came with. So we say that an object is going to be random if the smallest program that describes it is almost the same size as it itself, so it cannot be compressed. That's going to be the definition of randomness we are going to work with. And finally, it's a technical term that is that the measure is going to be prefix free if the computer model we are going to use does not have for any two programs, no program is going to be a valid prefix of another. So there's an issue with this measure of complexity, is that it might not describe what many commonly understand of complexity, because for this measure, the more complex objects are going to be the random ones. On the random ones, well, there's not much to say about them there. So there are other measures of complexity that use the concept of complexity as a base. One of these, the one that I want to use for this talk, is the sophistication. So sophistication divides an object in two parts. It divides one part is the program. That program is going to represent the structured information contained by the object, and at the input of the program, which is going to be the random information of the object. So one easy way to think about this, I think many of you know about regression. So we have a set of points. We have a simple linear model that attempts to describe those points. It not always follows the point perfectly. We have an error. So in this case, the program will be the linear function, and the random information is going to be like the error for each of the points. So that's an easy way to visualize this. So this is the formal definition for sophistication. So sophistication is going to be we have the program, we have this is simple, there are no components, and we have the object. So we're going to take the smallest program that computes the object. Now we have a constant C because we are going to allow some error. And the more the constant, the higher the significance is going to be for this measure. Okay? Now we're going to talk about, now that we know about the tools we are going to use, I'm going to describe an algorithmic characterization for adaptive behavior. So for this, I'm going to do a series of assumptions. So the object that we're going to study is going to be denoted by the letter M. So our object has a computable initial state. In this case, computable means that it can be produced or it can be described by the Turing machine. Then this object is going to evolve over time delta. So and this evolution or this dynamic is going to be also going to be computable. That means that this function, the function that maps the time to each of the states is going to be, can be described by a computer program. And that this object is going to attempt to live or survive into another system. The system E that also changes over time, delta. So our final assumption is that for adaptation and survival to be possible, we're going to assume that the object, in some way, in some computable way, since we are here in the computer universe, contains a description of the environment for each of the times. So this is the formal definition I'm going to use for adaptation. So we're going to say that the object that for time delta, the system is going to be adapted to the environment at the time delta if the conditional model complexity is less than a constant, is equal or less than a constant. So what does this mean? So this means that if the here will happen. So formally, there's going to be a program which that's given the object is going to be able to describe the environment at the respective time. And this program, I mean, is formally it's a computer program, but it can be described within a finite number of rules that are well defined. Now, this is I'm going to claim that our definition of adaptability is going to be robust. So we're going to be robust because this inequalities I gave you in the previous slide is going. It deals with any kind of computable method we try to come with that might describe how is the system adapted to the environment at a certain time. So if that method is computable, then we can define that inequality. Yes, like I said, this description can be any computable theory for an adaptation or a computable model for an organism that tries to predict the environment. And any computable characterization of adaptation that can be described within epsilon number of bits is going to meet the definition of epsilon adaptation, given a suitable choice of environment. So what do I mean by suitable choice of environment? You can think of the environment E as the adaptation condition for any given environment. So I'm going to do some examples of that. So let's start with a simple example. So let's say we have an organism, digital or otherwise, that in order to survive must find some food in a grid. So we have a grid, we have a grid, there's food on one of the coordinates, but it's going to find food in this pair of coordinates. So we assume the description of the organism is going to be codified by some kind of a computable way. For example, it could be a DNA or in this simulation it could be a computer program that describes the behavior of the organism. Then there's going to be a set of relatively specified unambiguous rules that govern how this information is used. So, well, it can be a logical theory, it can be a computable theory, anything that can be described with a a finite number of rules that are well defined is going to be able to describe a computable model. And we are going to say, in this case, the adaptation condition is that the organism can find the food at the coordinates. So, in this case, the environment E is just the coordinates. So we're going to say that the program, there's going to be a program that describes how the organisms find the food if the adaptation is possible. Now, we can do a jump of abstraction from this kind of models. So rather than asking to find a set of coordinates, we are going to ask for the theory that describes how this organism is fed to the environment to explain how is the organism able to find the food. So rather than asking the first coordinates, we are going to ask for the function that given the grid can produce the coordinates. And this can also be done with the definition that I just gave. And similarly, more complex computational structures and interactions can imply a field adaptation. Okay? Now, I'm going to talk about a long-format algorithm. So we say that an organism is going to converge. Well, this is a word that we use to describe this term. But this means that it's going to survive over an infinite number of times. If the condition of adaptation is going to be met, but an infinite number of deltas. So we're going to call this sequence of adaptation types. We want to call the sequence where this inequality is met the sequence of adaptation times, and the sequence under respective states of the system is going to be called the adapted states. And the program describes how this adaptation achieved is going to be adaptive behavior for the respective state. So let me jump to a concept in complexity theory. So we're going to talk about decidability. What is decidability? Decidability means that there exists a way to decide whenever this function is going to be met. And if this function is computable, there's a Turing machine or any kind of computer program that can describe this function, that can codify this function, then we're going to say that this function is decidable. So this function receives an input, the state of the system, and it's going to tell us that it's adapted or not. And this function must be complete. It must be defined for all possible states, for all possible inputs. So, and asking for this function to exist is equivalent of asking for the existence of a function that can enumerate all the adapted states, or a function that is going to tell us which are the adapted times. So if the function, if either of these three functions are not computable, then neither of the three are. Okay. Now let's go over some properties. So if we assume that the function that decides adaptability is computable, it can be solved by any kind of algorithm that you can define, then we have this inequality. So what this inequality is the complexity of the adapted time, of the adapted state, and the complexity of the adapted time itself is going to be bound by the initial conditions of the system, the state of the state of the system at the initial time, the complexity of the environment at the initial time, and the complexity of the underlying function. So it's going to be dominated by these three terms plus a constant term. well, this is a technical issue, a technical result for that, is that we can reduce the hunting problem to this inequality. And the previous inequalities give us the next proposition. So we have that if we have two computable systems that evolve over time, then over the same period of time, then they are going to be very close. That means that the complexity of the difference of the two systems at the time t is going to be bounded by just a constant term. So what does this mean? It means that in other words, time is going to eliminate absolutely the complexity, the evolution complexity of the system. The initial descriptive complexity is going to become increasingly relevant as time increases. That similarly complex initial states need to evolve into similarly complex future states over similarly complex time frames. And the consequences in more layman terms, we can say that if an ecosystem is computable and is not cyclical, the complexity of the evolution of the system follows closely that of natural numbers. That means that the increase of complexity of the system cannot be significantly faster than that of the natural numbers. So, what do I want to prove with that? So the previous proposition is going to apply to any infinite computable sequence or subsequence of a numerical system with respect of the index. So we have a numerical system that with adaptation times, delta 1, delta 2, etc., and a function that maps that maps each adaptation time to natural numbers. If that is computable, then the difference, then the complexity of the system at the time delta given by the dimension E is not going to be much larger than just giving the index that you want. So it's going to be much more complex than just natural numbers over time. So in other words, adaptation is definible, then the algorithm describes the complexity of the sequence of session times must follow closely that of the natural numbers. Okay. So from the final proposition, and then I'm going to explain this in more layman terms. So let's say that if we have a non-cyclical computable system with a computable initial state, an environment, and an infinite sequence of adaptation times, then if the function that describes the adaptation time is computable, then the adaptation times themselves are going to be computable. So this is what I mean by all the equations that I just gave, is that asking for computability, this is asking for the stability, asking for any kind of method that is going to tell us when the system is adapted to the environment. It's going to imply the computability of adaptation times and adaptation states. It's going to imply that there exists a way to enumerate the adaptation times, and the complexity of adaptation time themselves is not going to be much larger than the natural numbers. Okay, so now that I gave all the technical details, let's go to something more interesting. So now, when we work on this, we were working the problem for artificial life, that is called the problem of open-ended evolution. And the problem of open-ended evolution is how does a system, in this case, this issue for the field of artificial life, they want to be able to define systems that produce innovative, interesting life forms, let's say. And the conjecture that the community of artificial life has is that for a system, in order to show open-ended evolution, then it must be able to produce increasingly complex life forms, let's say. Now, Now there's two ways to, well, there are many ways to get the complexity, but there's a trivial one. So the trivial one is just that you can enumerate the natural numbers. You start with 1, 2, 3, 4, 5, 6. Now that sequence is going to contain all possible strings. So trivial is going to contain all possible life forms if we say that the life forms can be codified by in a computable way, a binary string or any kind of code you can think of. Therefore, trivial is going to produce any kind of complexity you want. So that's the trivial way of generating complexity or innovation in the system. You just generate all the possible answers, and you eventually going to have something. Now the problem is to find them, of course. So that since that definition is in that system, that trivial system can meet the weak definition of operator evolution. We propose a stronger definition for operator evolution. So what we are going to ask for this definition is that we are going to allow for drop of complexity, but that drop of complexity must not be as severe as that of natural numbers. Must be slower. That's what we are going to ask for. So this is what we are going to formally, what I mean by that. So we have a sequence of objects, computable objects. So this sequence is going to show operator evolution with respect to a complexity measure C, any kind of complexity measure. If for every time I, there exists J such that the complexity of J is larger than I. So we have a graph of complexity. We have a graph complexity over the sequence. Not all the states will grow, but there must have a graph of complexity. This is the weak definition of operator evolution. However, we're going to say that the sequence is going to show a strong operator evolution if, well, we have an increasing evolution, and if J is greater than I, then it's the function that's going to give the definite complexity. It's not grows significantly. So this formally is that this difference is not overbounded for any infinite subsequence. Okay, and as the direct consequence is very easy to come from all the previous propositions that I enumerated to this. So we have a weakly convergent system with an environment E, with adaptation times. Then it's going to exist a constant C, such that the measure of substitution for that constant. So that if the system, if the growth complexity is faster than this very slow growing function, then adaptation is going to be indecisible. This means that there's no method, there's no function, there's no formula we can apply in order to find when the system is going to be adapted. Well, this is a technical term for computability theory. This is a stronger way of indecisibility. This means that that we cannot even find that them by enumerating them exhaustively. And the adaptive behavior of the system is going to be irreducible and emergent. What do I mean by that? So we can here, I'm assuming that a system is going to be irreducible if we can find a function to generate the element of the system. So if we have a function that generates the element of the system, a computable function, then we find out, let's say, a reduction of that system, a way to describe it in simple terms. And furthermore, if the drop of complexity I'm going to allow are bounded, then this term that grows very, very slow, then doesn't grow at all. The system is totally undecisible. All of these are the consequences of the propositions that I gave in the previous slide. Okay, so we have I haven't put that, but there are conjectures. So the first conjecture is that the simulate is going to bound the growing complexity of any system to the rate of the lowest growing infinite sequence with respect to any adequate complexity measure C. Of course, the challenge of proving this conjecture is agree on what is an adequate measure of complexity.
Santiago, you're into your question time now, but we have a few minutes left, including questions.
Okay, yeah, I'm all done. And the final conjecture that the evolution of the complexity for any computable sequence is nearly identical to that of trivial systems. Therefore, computable sequences are the same as trivial. This is the same conjecture. So, what does all of this have to do with human mind? Okay. So, let me propose quickly a model for human mind. So, we can define M as a computable model for a human mind. E as an evolving task that the human M must complete. So, for example, it's a coder and it needs to generate a code for solving the tasks that are given by their boss. And we can define the behavior of the human mind or the task itself as complex if it meets the definition of open-ended evolution. So if we accept this model, these are going to be the consequences. If the mind is computable, then it can only keep up with no complex or trivial tasks, just enumerating on natural numbers. And if the mind can keep with non-complex or trivial tasks, then it's going to be incomputable. There's no Turing machine or computer program that's correct. Okay, so that's it.
Okay, thank you. Yeah, we have a few minutes for questions now.
Oh.
Yeah.
How could one experimentally test if mind is unpredictable?
Okay, we haven't done any kind of experiment here, but we have done some related experiments. Okay, this one. So this is a research article, and in this article, the team measured the capacity of the human mind to produce complexity in the terms of Cornwall complexity. What we find is that it peaks at age 25. So the human mind solved several tasks that were aimed to produce complexity, and we found that it peaks at age 25 and then it starts to decay. So this is not directed. It's not technically. It's not. Not directly linked to what I say, but this is a glimpse of what the algorithmic complexity theory can do for researching the human mind. Okay, any other question?
Yeah, it seems like the majority of the work is kind of more about a model of adaptive behavior or something. Would you agree? Like the human mind is sort of a special case at the end. But
yes.
In general, it seems to be a theory about describing a system adapting to its environment in terms of perspective.
Yes, that's right.
Okay. Do you think there's anything particular about human minds compared to other types of systems from your point of view?
Well, I mean, in this case, I'm assuming that we can characterize a human mind by an associated task. So we can analyze as a pair the human mind completing a task. That thing is correct. Now, the question is of course if the human mind is computable or not. So there's a big book by I forgot his name. But this is of course related to the question of if a strong AI is ever complex system, if we can are we going to produce a computer that is as smart as a human, whatever that means.
Okay, let's not go through again.